welcome to the first J. Mark Sowers Distinguished Lecture of the 2018-2019 academic year. It's wonderful to have all of you with us tonight for what should be a very entertaining talk by Professor Strogatz from Cornell University on the subject of natural synchronization. I'm Randy Heflin. I'm the Associate Dean for Research in the College of Science. I'll say a few words about this Distinguished Lecture Series, and then Lauren Child will introduce Professor Strogatz. Sally Morton, the Dean of our college, is very sorry that she's unable to join us tonight, but she does send her very best wishes to you all. The J. Mark Sowers Distinguished Lecture Series at the College of Science at Virginia Tech was initiated in February of 2017 with the goals of exchanging new and innovative ideas in science and providing opportunities for the university community and the general public to interact with eminent scholars. Mark Sowers is a longtime friend and supporter of the College of Science and Virginia Tech as a whole, and a valuable member of our college's Roundtable Advisory Board. Mark's passion for science and discovery and his exceptional generosity have made this wonderful lecture series possible. As someone who has had the pleasure of knowing Mark for several years now, let me just say that he is someone with remarkable curiosity, passion, cleverness, and creativity. Over the course of 2017, Mark made it possible for us to bring 5 eminent scholars to Virginia Tech, including Nobel laureates and members of the National Academies of Science and Engineering, as well as other very distinguished scholars. Mark is unable to be with us tonight, but I'm certain he'll be watching the video later. Please join me in thanking him for his tremendous generosity in creating this lecture series. Thank you, Mark. Next April, we'll have Dr. Patricia Kuhl from the University of Washington, who is a world expert on early language, bilingual brain development, and how young children learn. We're also in the process of finalizing 2 other talks, so please be on the lookout for announcements over the next couple of months. Now I'll ask Lauren Child, a faculty member at our Department of Mathematics, to come up and introduce Professor Strogatz.
But it is my great pleasure to introduce Professor Stephen Strogatz, the Jacob Gould Sherman Professor of Applied Mathematics at Cornell University. No stranger to the Ivy Leagues, he graduated with honors in mathematics from Princeton and received his PhD in Applied Mathematics from Harvard. Following time as a Marshall Scholar at Cambridge, as well as a National Science Foundation postdoctoral fellowship, he eventually settled at Cornell University, where he's now in his 24th year, I believe. A portion of which he spent, or I got to spend, working with him as his student, where he was my doctoral advisor. He's a pioneer in nonlinear dynamics and chaos, with multiple of his papers gracing the covers of the prestigious journal Science. In addition, he made a splash in network theory with his research on small world networks. You know, the networks that explains why it always seems there is someone who knows someone sitting next to you on the airplane ride. Incidentally, that work falls among the most cited papers in all of physics. For his accomplishments, he is recognized as a fellow of the Society of Industrial and Applied Mathematics, the American Academy of Arts and Science, the American Physical Society, and the American Mathematical Society. Beyond the accolades for his research, he received numerous awards for teaching and public communication, including the AAA Public Engagement with Science Award, whose other winners also include the likes of Carl Sagan and Neil deGrasse Tyson. You may also be familiar with him from his frequent appearances on Science Friday and on Radio Lab, or from his column on mathematics in the New York Times. In addition, he's author of several popular science books, including one entitled with the same name as the talk here, Sync. You might want to check that out afterwards. As well as authoring Nonlinear Dynamics and Chaos, one of the most well-regarded textbooks in nonlinear science. I've seen a few people ask him to sign a copy here this evening. It also so happens that that book appeared on the shelves of Peter Parker in Spider-Man, So, check that out. But his achievements are far too many to list in this brief introduction, as we'd actually like to hear from him this evening. So without further ado, it is my pleasure to present Professor Stephen Strogatz, who will tell us about the math and science of getting in sync.
Thank you very much, Lauren. Thank you, Mark Sowers, for this fantastic lecture series. I'm really honored to be here. Thank you all. Very encouraging to have such a full house. So as Lauren said, I'd like to tell you about how things in nature get in sync. And could we start with a little experiment, audience experiment? If I ask you to clap in sync, can you do it? Very good. So did you notice some interesting things happening here? Anyone? I see you're nodding. Can you tell us what things you observed?
We started very discretely out of phase and came into the sync, and then we sort of sped up once we were in phase.
All kinds of good observations. I don't know, good people in the back here started disparately, as you say, out of sync, came into sync, and then, for some reason, as audiences always do, sped up, and then stopped. Yeah, I don't know what that is actually with speeding up. That's a very common thing. I think it's that when people clap in sync, they're usually feeling like half the time they're not clapping. So couldn't we fill that space too? So then they speed up and it's disorganized quickly though. Yeah, so as you can see from that little demo, it's pretty easy to get in sync. People don't have any trouble getting in sync. It's easy and it's for some reason fun. We like it. It gives us pleasure. And so we do all kinds of things for fun involving sync, like singing together, dancing, that's kind of sync. You're moving your limbs in sync with somebody else, feeling some emotional resonance with them, maybe. Even something like marching, as crude as that is, I probably shouldn't say it that way, but just stomping around together is enjoyable. So because it's so easy for us, I think we tend to underestimate what a miracle is. That is, it seems like the most natural thing in the world. But what exactly is required to be able to get in sync? Do you need to be a human being? Do you need to be alive? Well, actually not. So here's an example. This might be the first scientific example where sync was studied carefully. Goes back to 1665. That's Christian Huygens, Dutch astronomer, mathematician, physicist. And he was sick one time. It seems he was sort of frail from what I can tell. He often had stomach trouble. And he tells a story of how, one of the things he's famous for is inventing the pendulum clock. Galileo had ideas about pendulum clocks, but the first really good working pendulum clock is due to Christian Huygens. And he had two of them. He built two because he had the idea that he was going to solve this famous problem, the longitude problem. You may have read a book about that, where he was going to put these clocks on boats that would go out to sea, and in effect, by carrying the time of the home port out to sea and then consulting the sun, the theory was that you could figure out what your longitude was on the oceans, which otherwise was a massively important unsolved problem at the time. Anyway, so he had these two clocks, one for a backup and one for the real thing. And but he happened to notice as he was lying in his room, feeling his usual intestinal problems, that these clocks were doing something he didn't expect, which was that they were swinging, their pendulums were swinging in perfect antiphase. So that is, one would go this way and the other would go the other way. So they'd move back and forth, almost like clapping, except they were separate clocks. And he had no idea why they would be in this antiphase synchronization with each other. That is, they wouldn't just do it at random. There must be something going on, some way of communicating. And so he suspected at first that maybe there were some gentle air currents, that they were somehow signaling each other. And so he put up a big blanket between them to block any air currents and found that they were still in sync. So it wasn't air. Then he realized they were actually both attached. They were kind of hanging from the same beam, a wooden beam. They were hanging down from it. And he thought maybe they were somehow jiggling the beam or sending vibrations through the beam and communicating that way. So he took one of them off the beam and moved it away, and sure enough, within a few seconds, they fell out of step. So there was something going on with this essentially imperceptible signaling that was enough to keep them in sync. So I want to show you the modern day version of that. You may have seen this video I'm going to show next. It's on YouTube, has many hundreds of thousands of views, maybe 1 million views. It's the modern day reenactment of what Huygens observed, except it's using metronomes, like a musician would have to keep time. And I think it'll speak for itself. Let me just show it to you. So I have not really figured out how to embed my videos very well. So I'm just going to, sorry, John. Just going to jump out and hope that this will work. I'll jump back in a minute. Okay. So let's see if this will play. All right, what you're seeing there is 5 metronomes on a wooden platform. These are empty cans of Coke or other soda, whatever. Doesn't have to, it works with other, fresh cans. But anyway, so you'll see the purpose of these empty soda cans in a minute. But first, let's see what this student does with the experiment. Oh, I see. It's starting in the middle of the, let's go back here. Yeah, it's more interesting here. Notice they're not on the soda cans. They're just lying on just a platform, like a piece of wood on the table. Now he's going to start them in no particular way. So let me make sure you got what's happening so far. Basically nothing. Right? When they're just doing their own thing, they don't get in sync. They're not communicating through that board. They're not communicating through the table. They're just disorganized. You can hear jiggity, jiggity, jiggity. They don't have any particular pattern. Now watch what happens when they're on the empty cans. See that one guy? You probably know someone like that. This one right here. So he's not cooperating, but he will. He will soon become a conformist like the rest of them. Right, so I won't play the whole thing. It does not unlock itself, it just stays. Are you noticing anything happening with the board? The board is moving, right? That's the point of the empty cans. The board is moving a little bit sideways, and somehow by being on this accelerated platform that's jiggling sideways, they're now in physics speak, they're in this non-inertial frame, they're now moving, and somehow that's putting enough forces on them to keep everyone in step. Actually working out the mechanics of that is pretty tricky. I would say that's still sort of an unsolved math problem. To show that the laws of classical physics will imply this, no matter how you start them. Because for one thing, metronomes are kind of complicated to describe. They're not just simple pendulums. They have extra, machinery in them that kind of keeps them at a certain amplitude. They'll go for a long time. Anyway, it's an interesting thing, but I hope you can see you don't need to be alive to get in sync spontaneously. Inanimate things as simple as metronomes can do it. Okay, so let me get out of there, back here. Okay. Yeah, so that was Christian Huygens. There were the metronomes. Now, you may be wondering, is that the best I've got? Who cares about that? Why is it important to even study this subject? Well, for one thing, your life depends on it. That should convince you, I hope. That is, you've got cells in your heart, the pacemaker cells in your sinoatrial node, which are electrical oscillators that are always, for the whole of your life, putting out voltage oscillations that have to be in sync with the other 10,000 cells in your sinoatrial node so that they can send a coherent signal to the rest of your heart, to your ventricles, to pump blood to keep you alive. And this will happen, if you live to be 80, it will happen about 3 billion times in your lifetime. So, and you don't want to screw that up. You'll notice your heart fluttering, or it could be worse than that even. So your pacemaker cells do this your whole life quite reliably. And also when you think about your own sleep rhythms, if you have jet lag, you're out of sync with the world. When you have a healthy sleep cycle, not only are you in sync with the world, but also all your internal rhythms are in sync with each other. You've got your body temperature going up and down when it should, your hormones are being released at the right time, you're ready to eat when it's time, you're alert when you should be. So if you are a person who works the night shift and then suddenly switches to day shift, you'll learn what it means to be out of sync internally, or when you travel across many time zones, we all experience this. But so being in sync is important for health and general well-being and good function. There's also things you may not be aware of happening right now in your pancreas. Also, it's hard to tune into our pancreas, but the cells that secrete insulin have their own electrical oscillations, and if the pancreatic beta cells are not in sync, they don't really work correctly and could be quite bad for you. Now, there's also cases where sync is not helpful. It can be harmful in some cases. Sometimes it's not harmful or helpful, but just mysterious. Some of you will know what I mean. If, like, you happen to have your period in sync with your best friend. This happens commonly. And we don't exactly know why that happens or what's causing it. It seems that there's a pheromone in sweat. So there are unbelievable but true experiments that have been done where one woman who noticed that whenever she went home for the summer, her sister's period would immediately synchronize to hers for the rest of the summer, no matter how they were, during the school year when they were not together. There was a suspicion that this woman, Genevieve, had some kind of powerful synchronizing substance in something about her, and the suspicion was it might be in her sweat. So researchers asked her to wear cotton arm pads, and they collected her sweat secretions every day for a significant period of time, and then kind of, extracted the sweat, and made a kind of eau de Geneviève, some kind of potion that they then put, this is true, I could give you the citation if you want to look this up. Put the sweat on not just the raw sweat, but so it doesn't smell. They mix it with some alcohol, it's odorless, but they put this little potion on the lip of a woman who had never met Geneviève, not related to her, miles away, who, you guessed it, started to synchronize her menstrual cycle with that of this woman. So there is some unknown substance in sweat that conveys enough information about the phase of the menstrual cycle that people who spend enough time, women who spend enough time, in close proximity, and often it helps if you're friendly. It seems that there are studies that if this is your enemy or otherwise an antagonist, there's somehow the body knows that and tends not to get in sync with the antagonistic. So that's not quite understood yet. But I should say, this work is controversial. There are researchers who don't believe it at all and say the statistics were not done very well. So you might want to look into this if you find it interesting. I tend to believe it, but there are people who are skeptical about the literature on menstrual synchrony. It's certainly well documented in many kinds of animals. I mean, all mammals exhibit it, so it would be surprising if people didn't, but it seems that we do. There's also a case of truly pernicious synchrony that can happen in your brain. If your brain cells start discharging in lockstep, that's the disease that we call epilepsy. When you have the rhythmic convulsions associated with seizures, that's too many brain cells firing at the same time that really shouldn't. So there's all these medical aspects of why we should care about sync, but I want to touch here on a more philosophical aspect of it that I hope will interest you, which I think you could consider an eternal question about order in the universe. How does order emerge out of disorder? How does order emerge out of chaos? I think you can see from this example with the metronomes that it certainly can happen on its own. Well, we still, as I say, don't fully understand how the metronomes are doing it. This kind of question goes way back in history, and so I want to discuss another example of it which has to do with the creatures that we call fireflies. They're actually little beetles. You probably have them here, like we have. Okay, we have them up in New York State too. They're flying around usually in open meadows. In June, you see them a lot throughout the summer. And in Southeast Asia, especially, like places like Thailand or Malaysia and New Guinea, there are spectacular displays of thousands of fireflies all flashing together. And this is not something that our fireflies typically do. The rugged individualists here in the US do their own rhythm. I suppose we could make an equally bad joke about cooperative spirit of Asian fireflies, but leaving that aside, since that one got no laughs whatsoever, it probably doesn't deserve any. There are these amazing examples of spectacular rhythmic synchrony of fireflies in that part of the world. There are some actually here in like the Great Smoky Mountains. For a long time it was thought they did not occur in the US, synchrony of fireflies, but they do. They have them. Actually, I once was quoted in an article explaining how they don't occur here, and a woman wrote to me saying, "I'm reading the article and I'm very confused by this because I'm sitting on my porch, as I do every summer here in Knoxville, Tennessee, and I'm looking at what we call the light show, and for generations we have referred to it as the light show. And here are fireflies flash and sync. And they do it, and she went on to describe 3 times in 2 seconds, and then this many seconds quiet, and so on. And I thought, she really sounded like she knew what she was talking about. And because sometimes people will say, oh, I've seen fireflies and sync, but they don't really know what they're talking about. But she did know what she was talking about. And I suggested to a firefly researcher named Jonathan Copeland from Georgia Southern that this person sounds legit. Maybe you should go look at this. And he went up there, and in Elkmont, actually, Tennessee, where Lynn Faust is the name of the person who observed them. She gave the first documented case of firefly synchrony in the Western Hemisphere. And it's now become a big tourist trap and tourist attraction. People go to Elkmont to see the Lynn Faust's fireflies, and they do this every summer, except that there's a problem with people trampling on the places where the fireflies like to put their eggs or whatever they do, I don't know. And so it's probably going to not be a good thing for much longer. So if you want to be like the last wave of tourists, go see this. Elkmont, Tennessee, the fireflies of Elkmont, the only ones we know of in the U.S. But anyway, okay, so let me now talk about it. The ones in Asia, the question is, again, how is it even possible that they're doing this? So let's talk about it a little more. There were many theories about how it might be possible in the beginning of the 20th century. And here's a person writing in Science magazine. There were about on the order of 20 articles about this phenomenon in the years between about 1900 and 1920. And so here's one person with his explanation. He says, as you've probably already read, some 20 years ago I saw or thought I saw. I guess he figures maybe it's some kind of illusion. He's leaving that option open. I saw or thought I saw a synchronal or simultaneous flashing of fireflies. I could hardly believe my eyes, for such a thing to occur among insects is certainly contrary to all natural laws. Okay, not so clear what that would mean, what natural laws are being violated. But I'm guessing that the person is thinking, yeah, anyone have a guess? What would be the natural law that you might say is being violated by synchronous fireflies? Can you think of any? No? Nothing? What do you think the guy meant? Willfulness. That they don't have enough willpower to do it? They're not conscious? Entropy, I think, is, I don't know. We don't know what the person was thinking, but I'm guessing entropy. That the idea in the second law that things go to greater disorder, not spontaneously to greater order, maybe that's the law. I don't know. Anyway, but this person did have the explanation. He says the apparent phenomenon was caused by the twitching of my eyelids. The insects had nothing whatsoever to do with it. So that's Philip Moran, 1917, twitching eyelid theory. Okay, well, now, another aspect of this is that some people think if you get in sync, it's because there's a leader. People are following a conductor of the orchestra, or the fireflies are following a maestro firefly. And so George Hudson came up with a theory like that a year later. Is there a leader? He says, well, if it's desired to get a body of men to sing or play together in perfect rhythm, they not only must have a leader, but must be trained to follow such a leader. So not just enough to have a leader, you need training. Do these insects inherit a sense of rhythm more perfect than our own? Apparently, George Hudson doesn't think that they do. And, you know, there have been attempts to find a leader, and you could imagine biology would not do it that way. You know, like what if a bird eats the leader, the whole thing is going to fall apart? That's not a very robust design if this is important to them. So that didn't seem very plausible either. There were many other theories about how the fireflies could be doing it. Some people thought it was related to the weather. You know, like on exceptional calm nights or humid or dark nights. What does a dark night mean? I guess no full moon, so maybe they can see each other better. Or maybe here's one idea. After all, it's happening in Southeast Asia. They have lightning storms. It's the jungle. You know, maybe it's lightning. Like the lightning goes off, all the fireflies flash and startle from the lightning, and now that they're in sync, they just stay in sync. Okay, so someone who has, actually an American naturalist who had lived there in Southeast Asia for a long time, gave this assessment that some of the published explanations are more remarkable than the phenomenon itself. Anyway, it continued to be a mystery until the 1960s. But before I tell you what we now think is the explanation of the mystery, let me show you what it really looks like. And for this, I would like some help turning out the lights. You can't really see the fireflies unless it's very dark. Hold on, don't turn them off yet. Because I want to jump out of here and get my video rolling. This is from one of David Attenborough's wonderful TV shows. I think I'm probably okay now, so go ahead and let her rip. All right, so he's going to, oh, well, we could do it the moderate darkness. That may work. Or we could go fully dark, let's see.
Sound is not the only way of communicating at night. When the sun goes down here on the tidal rivers of Malaysia, the trees on the banks become alive with animals communicating with light. At first, there are just a few twinkles in the branches, but about 3/4 of an hour after sunset, the show begins. These are fireflies, thousands and thousands of tiny beetles only about 5 millimeters long, each sending a message in Morse code with a lantern in its hand. The luminos that are flashing are males, and their message, of course, is directed to the females, and it's a very simple one. Come hither, mate with me. This particular species, as well as one or two others here in Southeast Asia, reinforce that message and make sure it's sent the farthest possible distance by all flashing in perfect time together, in perfect synchrony. And the result is that even after I've drifted many yards downriver, looking back, I can still see that tree alkaline with pulsing light. This display continues throughout the hours of darkness every night of the year and extends for miles along the river. The combined light of all these tiny beetles is so bright that fishermen out at sea can use them as navigating beacons to guide them back to their home rivers. Only in Southeast Asia do fireflies coordinate their flashings in this spectacular way. Elsewhere in the world, fireflies operate independently, each beaming its own individual invitation to mate.
Okay, could I have the lights back on, please? Thank you. Any reaction to what you saw or comment? Yes, please.
Was there a wave-like pattern?
Was there a wave-like pattern? That's what I was hoping you would say. Did people notice that? Right? It doesn't, he says they're all in perfect time, in perfect synchrony, and yet there's a clear thing when they pan back from the river, you see what looks like a wave shooting down the river. So it's clearly not perfect synchrony. You can see it with your own eyes. However, it's not random. There's clearly, like within the scale of a given tree or a few trees, it's pretty organized, but they're not in perfect sync from tree to tree. So it's a little bit exaggerating to say perfect synchrony, but there is definitely some kind of coherent phenomenon happening. It's not totally clear to me whether it's a wave or whether it's just that an individual tree is well organized and another tree is at a different phase, and you get a feeling of waves. When you digitize it and really look at it in slow motion, it doesn't really look as much like a wave as more like, a tree or a few trees are in sync, but they're not in perfect sync with ones farther down. Yes?
So could it possibly be that they're seeing the other tree and there's a delay in which they can actually activate their light? So they're activating when they see it, but there are the other branches or the other bush is already deactivating.
It's a very nice explanation you're giving, right? So there certainly could be physiological delays from processing the signal and getting your flash organ ready to go and so on. And so maybe these delays would account for the wave-like picture there. That they're seeing each other and triggering each other. That is basically what we now think is going on, more or less. So let me go into a little more detail about that. We know that that's basically what's happening. So let's see here. Yeah, okay, so we don't want that. Right, so how do they do it? They do it themselves. They organize themselves. They are aware of each other, and the evidence for it comes from research by John Buck and Elizabeth Buck, who were a married couple who worked at the NIH in Bethesda. And on one occasion, in the 1960s, they went to Thailand, actually Bangkok, and had a guide take them out to the river where the best synchronizing species were known to be. And they then collected bags full of fireflies and brought them back to their hotel room in Bangkok and started doing experiments on them in the hotel room, turning out the lights. And then they later were able to keep them alive well enough to study them back in Bethesda. And here's what they were finding. That first of all, as probably wouldn't surprise you, fireflies flash rhythmically by themselves. They have a rhythm, and that's already very informative. They're not just flashing randomly, they flash rhythmically, which tells you that there must be some kind of internal clock in the firefly's nervous system. They're able to keep time. They have a constant tempo. So there's something in its little brain or its little, whatever its nervous system is, that's sufficient to time its flashes. So the question then becomes, if they've got clocks inside themselves, what are the rules of the clock? And they did what biologists always do, which is a stimulus and response kind of experiment. They're going to poke it and see how it responds. In this case, they don't poke it literally. They poke it with a flashlight, in the sense that if I want to simulate another firefly, I take a little pen flashlight and I flash it at this firefly and then see what will happen. So when they did that, they find that the firefly on the receiving end adjusts the timing of its flash in response to an incoming flash. It will, that is, compared to what it would have done if not disturbed, it will flash either a little sooner than it would have or a little later. And the details depend on when exactly you stimulate. So the amount of the adjustment that it makes depends on where you stimulate it in its flash cycle. Like if you flash when it's flashing, that will produce one kind of response. If you flash halfway between its flashes, that produces a different response. And so the response in terms of phase shift as a function of when you gave your stimulus can be graphed out, and it's a mathematical function. Like you learned about functions in middle school or high school, or I guess pre-calculus maybe. There's a case where you're using a function to understand the flash response of a firefly. And so what they figured was happening is that firefly flashes, another firefly sees it, adjusts its flash, and they're all seeing and flashing at each other, and so there's all this complicated interaction, and somehow out of that, synchrony occurs. Except that's the part that's math, not biology. How is it that the iteration of these rules over hundreds or thousands of fireflies inevitably leads to them getting in sync? That's not something a biologist is trained to answer, but mathematicians are, and although it's a hard problem. So that was one of the things I had worked on myself, was a simplified model of fireflies showing that they would all get in sync under certain conditions. And so that is what we sort of think is going on now, that that's how it works. But the work that I did on that was based on work by someone long before me. This question of how you get group synchrony is a new kind of math problem. At least it was new in the 1960s. It's not really new anymore. But it was then. And it was first studied by this gentleman, Art Winfrey, back in 1965, when he was a senior in college. So that's not his yearbook photo. That's him much later in his life. But I don't have his yearbook photo. He actually was a student in engineering physics. So he was not a biology major. He was doing something like this wonderful program that you have here at Virginia Tech in systems biology, led by, or maybe partly initiated by my friend John Tyson, that, you know, combining the insights that you can get from physics and engineering and math and computer science with the questions that biologists and doctors like to ask, that's the kind of thing that is really cutting edge systems biology that's happening right here. One of the few places in the world, actually, I don't know if you know, that has an undergraduate systems biology programs. You should be proud of that and start swarming to it, if you like math and biology especially. But anyway, Winfrey didn't have access to such a program. It didn't exist in those days. But he did study engineering and physics and was interested in biology. So he was kind of doing it himself before it was fashionable. And, oh yeah, he did go to Cornell. But that's not really relevant. But then he went on to become quite a recognized scientist. In 1984, he got a MacArthur so-called Genius Award. His son, Eric Winfrey, who I knew when he was about 12 years old, also won a MacArthur Award. There aren't too many father-son or, you know, parent-sibling, parent-child, double MacArthurs, but they were one. Eric Winfrey's now a professor at Caltech. Anyway, so yeah, Winfrey had a good life scientifically, and I want to give you his basic insight without going into too much of the math, but just the pictures, which is that he essentially thought of the problem this way. Think of a biological oscillator, which you could say that's a firefly flashing or a heart cell firing or any other thing going through a rhythm, as being like a runner, running around a track. And so in this picture, the track, the circular track, is supposed to represent the cycle of biochemical states or whatever it is that's oscillating, voltages going up and down. Going around this cycle is like running around a track. That is, when you complete one lap, you've gone through one full cycle of the oscillation, whatever it is. Then, if you imagine a tree full of fireflies, or a sinoatrial node with its 10,000 cells, that's like a group of oscillators. That'd be like a club of runners, all running around the same track. And I say a running club because, you know, like in any club, there are going to be people who are faster and slower at running. So that'd be like the different frequencies or periods of the oscillator. Some are inherently faster than others in going through their cycle. But suppose that these are friendly members of the club. They would like to run together as a pack. That's some measure of their friendship strength. You know, how important it is to the fast ones to slow down and run with the slow folks. And how much do the slow folks want to make the effort to keep up with the fast ones so that they can run together. That's in math terms. We would measure that by a quantity we call the coupling strength between the oscillators, a parameter that measures how strongly they pull on each other. And so you've got this battle between the inherent diversity or differences in their frequencies and the synchronizing tendency of the coupling. Okay, so the big question then is, can the runners overcome their inherent differences to form a synchronized pack? And so what you might think intuitively would happen in this situation is, as you crank up the coupling, the more they interact, the more synchronized they'll get. But what Winfrey found is that that wasn't really true, that it was more subtle than that, and that the emergence of synchrony in a computer model that he built showed a phase transition. So a phase transition is the kind of thing he was learning about in his engineering physics classes and taking solid-state physics. But he was seeing it in his mathematical model in biology. So what I'm showing here is on this vertical axis, it's a measure of how synchronized the population is. from 0 to 1, fraction of runners running at the same speed. That's 1 would be perfect sync and 0 would be totally out of sync, or what I'm calling incoherent. And then on this axis, let's imagine a thought experiment where you make the runners more and more homogeneous going this way. So I'm trying to show it with this cartoon where here's a very diverse group of runners shown by their different shapes. You might tend to think this long-legged dude might be fast. However, notice that he's at the back of the pack. And this person is actually in the front. But whereas then, as we make them more and more similar, this bell curve is getting narrower and narrower. What happens is, at a critical level of homogeneity, you go from having absolutely no synchrony to suddenly starting to have synchrony. And it gets stronger and stronger as you go past that critical point. So this analogy where there's a critical level in the population of diversity that acts sort of like a freezing point, where something dramatic suddenly happens after that critical point. That was a surprise and unknown at the time, and this was, like I say, something he discovered as an undergraduate. By the way, maybe it's a good place, since I see lots of undergraduates in the crowd, to emphasize how important it is to be young and optimistic and maybe a little, well, what word do I want to use? Like foolish, ignorant. What I mean is, naive would be a more pleasant word. Yeah. I only mean, when I say ignorant, I don't mean it in a disparaging way. I mean, you don't know what's impossible. It's really helpful to not know what's impossible. If you'd asked any older researcher, they would have said, you cannot study a population of 1,000 oscillators in a computer that are nonlinear, that have random frequencies. I mean, we could, if you look at the math books of that era, people were studying 2 and 3 such oscillators. They're also nonlinear, if that means something to you. These are not the simple harmonic oscillators you learn about in first-year physics. These are oscillators that have a preferred amplitude that they always go back to. They have to be, in the jargon, nonlinear, which makes them essentially impossible to solve with formulas. So you've got to somehow find a way to get insight into an enormous population of nonlinear random frequency oscillators. And that is a good recipe for an impossible problem, except that Winfrey solved it by just being young and naive and optimistic and having a great idea. So it was a revolutionary thing at the time, though it was kind of unnoticed. I mean, it was an undergraduate who did it, so nobody was really even aware of it. But about 10 years later, after Winfrey did publish his first scientific article where he explained what he was doing, this great physicist, Yoshiki Kuramoto in Japan, realized that Winfrey had done something marvelous and built on it and cleaned it up. Instead of Winfrey's computer simulation, Kuramoto wrote down a system of differential equations, which I'm writing down here since I was invited by the math department. Want to earn my bread here a little bit. So there's I think the only equation I'm probably going to show in the whole talk. But just to translate it for people who are rusty on their nonlinear many-body differential equations. So theta is supposed to be the position of a runner running around a track, be an angle or a phase in a cycle. D theta dt is how fast is it running around the track. It's its angular velocity. It has a subscript I because there's a whole population of them. Think of n as 1,000 or 10,000 oscillators. They have different natural frequencies, as I said. The omega I is their inherent speed at running around the track. And then there's this part, which looks like a complicated part, which is all the interactions. So this is a physicist's way of writing down, look at this term, theta j minus theta I. It says if runner j is a little ahead of I on the track, then you're supposed to compute the sine function of that. And suppose that the number is small, theta j minus theta I. So if it's a sine of a small positive number, that'll be positive. And what that means, and take this number k, the coupling strength, to be positive. So basically what happens is, if j is a little ahead of I, it gives a little push to the guy who's behind saying, hurry up and speed up. And conversely, if you're ahead, this kind of term tells you, slow down, you're running too fast for me. So that's what this sine function is doing. And then you'll notice an unrealistic looking thing here, which is that everybody is sensing everybody else. J is it's not just looking at nearest neighbors or anything like on the fireflies on the riverbank where they can only see trees near them. Here, everybody is coupled to everyone else. It's not realistic, but if you have any hope of solving the math of this, that's where you would start. That's always known to be the simplest case. In the jargon of statistical physics, we would call it the infinite range approximation or mean field theory. So it's the most tractable case for the math. Anyway, Kuramoto, through being a fantastic mathematical physicist, was able to solve this problem mathematically. He did not even simulate it on the computer, just did it in his head with pencil and paper and cleverness. I didn't emphasize these omegas are those random, those are the bell curves that I was showing you, the random frequencies. And so what the point was that he was able to calculate Winfrey's phase transition analytically and understand and explain exactly what Winfrey had seen in his computer simulations. So if you like this kind of stuff and want to learn more, this is the problem I've been obsessed with for about now 30 years, and I've written lots and lots of papers about it. And I'm still in love with it and can't leave it. Got to keep thinking about it. It's just a bottomless pit of endless, interesting math. But what I want to do next is tie this to something very much less abstract and bring in some engineering. So far we've talked about people clapping here in an audience, metronomes, fireflies in biology, runners on a track, Winfrey's statistical physics and phase transitions. Now let's bring in some stuff with real people in a real life situation. And it has to do with this. This will be my final example for today. You may have heard about the Millennium Bridge in London. Any people here have walked across it maybe on a trip to London? Couple? Yeah, it's a very pretty bridge. As the name suggests, it was built in the year 2000 to commemorate the millennium. There was a big contest actually to design a new bridge across the Thames, the first one in 100 years, first new footbridge. And this was the winning proposal from Lord Norman Foster, considered one of the greatest architects in the world. So Lord Foster put in this design that he called the blade of light. It's like a thin ribbon, very minimal structure. I don't know if you can tell what you're seeing. It's a suspension bridge. If you're not used to thinking about bridges, you might think that these piers are holding up the bridge. Not really. What's happening is that these are holding up these tension cables. Basically what you should think of is that there's these two arms like that, and now you string guitar strings across the Thames River, really taut, okay, like a guitar string or a piano string or something. So you hang all these tension cables perfectly straight, unlike a normal suspension bridge where you're used to big droopy cables like that, and then the bridge deck hangs from those. This is just these wires across the river, totally straight as you can make it, and then you hang the bridge from that with these little whatever they're called, underneath the deck. So it's an outrageous way of making a bridge. And it was deliberately outrageous. It was supposed to be very modernistic and minimal and beautiful. And it is, and if you've walked on it, I think you would agree. You get fantastic views of the river and the city. You got St. Paul's Cathedral right there, and on the other side, there's the Tate Art, big Tate Modern Museum, very nice. Anyway, so everybody's all proud. We got this beautiful new bridge. It's opening day. The Queen is there. The BBC is there. They had to close the bridge 2 days later because something happened on the bridge that nobody expected, that the engineers didn't know about, that nobody knew about, that has to do with our story of synchrony. It has to do with a story of unintended synchrony caused by human feedback with a structure, in this case the bridge. So I'm going to clarify exactly what I mean by that as we go. Let's see. Maybe it's best if I just do a slight demonstration. Well, I don't know if I need to do a demonstration. I got 2 interviews for you to show from the BBC where, it was a terrible embarrassment, you must realize. And it cost many millions of pounds to fix the bridge afterward. It does not wobble or do anything weird. If you go on it now, it's totally steady. It's kind of boring, actually. It was more interesting. It started to wobble sideways. That's what happened. That's what no one expected. Let me just have you watch these interviews. The first interview you're going to see is with a ruthless interviewer from a TV show called Science Shack that the BBC produced. And he is about to, actually, I think he's not so ruthless maybe in the first. He just talks to some people who were there on opening day. So he's in kind of good behavior. He just asks a little boy what happened, and he asks an old man what happened. All right, so watch, and they'll try to describe what's going on that day.
thread is started moving sideways and slightly up and down, rather like being on a boat.
Yeah, it felt unstable, and it was very windy. And I remember it had lots of flags up and down the side, so you could definitely, there was something going on sideways, it felt, maybe.
Not up and down, and not forwards and backwards, just sides up. About how much was it moving, do you think?
That was about,
That much, or this much?
about a second.
This much?
Yeah.
At least 6 to 8 inches, I would have thought. Yes.
Right, so at least this much.
Oh, yes.
I remember wanting to get off.
Oh, did you?
Yeah, and it
So
felt
it's enough
hard.
to be scary.
Yeah, but I thought that was just me.
Tell me why you had to do this?
You had to do this because to keep you balanced. Because if you didn't keep you balanced, then you'd just fall over about, like, to the left or right, about 4 to 5 degrees.
So just show me how you were born. Right. And then show me what it was like when the bridge started to go. Right, so you had to deliberately push your feet up sideways.
Yes.
And short steps.
That's right. Yes.
Right.
And it seemed obvious to me that it was probably the number of people on it.
Were they deliberately walking in step or anything like that?
No, they just had to conform to the movement of the bridge.
All right, so now I want you to concentrate on that last remark. In response to the question, were they deliberately walking in step or anything like that? The gentleman says, no, they just had to conform to the movement of the bridge. Okay, so what he's saying is, as you're going to see in the next video, the bridge starts moving sideways for reasons that are not really clear. When something's moving sideways and you're walking on it, it's very uncomfortable. If you've ever been on a train that's going fast, or maybe a subway going fast, if it starts shaking sideways, people go like this, right? They just put their feet out wide. They start to do a kind of penguin walk, like this, and it feels safer. And also, if the bridge is moving, people start to walk in step with the bridge, as the little boy says, to keep your balance so you don't tip over by 45 degrees. Okay, now you're going to see people doing that. And the part that has to do with interesting feedback is that when people walk like this, they put significant sideways forces on the bridge, more than they would normally. Now, usually bridge engineers don't think about sideways forces. You might be thinking, I've heard about bridges that oscillated because soldiers were marching in step, right? That's a classic example. That is not this. Every engineer knows that. That's engineering 101. And bridges have collapsed from soldiers marching in step, causing a vertical resonance where the bridge goes up and down at its resonant frequency. You know, because the bridge was incorrectly designed, so its frequency matches the frequency of human walking. And if you hit the vertical resonance, yes, a bridge will collapse, and armies have fallen into rivers because of that. So all generals know, don't do that, don't march in step across a bridge. All bridge engineers know you don't make a bridge like that. But when you put your feet down, that's a very significant downward force, not very much sideways force. Okay, nobody ever teaches to worry about the sideways motion of a bridge, because people walk out of step with each other. There's no reason for people to be in sync. They're just pedestrians on the Millennium Bridge, old ladies and little kids, and they're not in sync. So nobody ever thought about, let's make sure we don't have a sideways resonant frequency that matches the frequency of human, penguin walk. So that was the problem on the Millennium Bridge. As you'll see, that the people start doing this, they start doing it in sync because they got to get in step with the bridge's motion. Now that they're all in sync, they're really pushing the bridge, which makes the bridge move a lot, which makes any last holdouts to start going like this. And so you'll see it happening. They had, as I say, the BBC was there on opening day, so we have this on film. All right, so that's the next video. And also you'll see a deceptive interview. This is the part where I think it's a little brutal. The interviewer talks to first the bridge engineer, the head engineer on the project. A young guy who must have been so happy to have the honor of leading the team to make the Millennium Bridge, and now he's got to talk to this interviewer about what went wrong. Then you'll see an interview with a guy I've collaborated with named Alan McRoby, who is a civil engineer at Cambridge, who had an insight into how to simulate the bridge. He made a kind of small-scale model of what's going on the bridge that really clarifies what the problem is. But the confusing part is the interviewer says, Alan, this is all your fault, isn't it? It's not his fault. He's the one who's solving the problem. He didn't build the bridge. Okay. Okay, not this one. Sorry.
Side.
Let's do bridge sway. Yeah. All right.
So that was a Did anyone get hurt? No. Right. So it was quite small, but real. Absolutely. You thought, oh, bother.
I felt I was disappointed about it. We spent a lot of time designing this bridge, and we'd analysed it, we'd checked it to codes, to heavier loads than the codes, and here it was doing something that we didn't know about.
Yeah.
The most dramatic and shocking footage shows whole sections of the crowd, hundreds of people, apparently rocking from side to side, defending each other, but with the bridge. This synchronized movement seemed to be driving the bridge. But how could the crowd become synchronized? Was there something special about the Millennium Bridge that caused this effect? This was to be the focus of the investigation.
Well, at last, the simulated bridge is finished, and I can make it wobble. Now, Alan, this is all your fault, isn't it? You designed this, yes? Yes. Simulated bridge, and this, you reckon, mimics the action of the real bridge. It captures a lot of the physics, yes. Right, so if we get on it, we should be able to wobble it, yes?
Alan McRoby is a bridge engineer from Cambridge who wrote to me, suggesting that a bridge simulator ought to wobble in the same way as the real bridge, provided we hung it on pendulums of exactly the right length.
This one's only a couple of tons, but so it's fairly easy to get going. Well, it's certainly walking. It's certainly going now. It doesn't have to be a real vandal, just walk. But it starts to go. It's actually quite difficult to walk. You have to be careful when you put your feet down, don't you? Because if you get it wrong, it just throws you off your feet. It certainly affects the way you walk, yes. You can't walk normally on it. No, if you try and put one foot in front of another, it's moving your feet away from under you. Yeah. So you've got to put your feet out sideways.
So already the simulator is making me walk in exactly the same way as our witnesses walked on the real bridge. For a more convincing experiment, I wanted my own opening day crowd, the Science Shack team. Their instructions, just walk normally.
It's really intriguing because none of these people is trying to drive it. They're all having some difficulty walking. And the only way you can walk comfortably is by getting in step. But then, of course, everyone is driving the bridge. You can't help it. You're actually forced by the movement of the bridge to get into step and therefore to drive it to move further.
So believe it or not, that kind of thing is still a problem. Not so much on the Millennium Bridge. That was fixed by putting shock absorbers under it to increase the damping. So it doesn't do that anymore. But there are still reports every few years of some, fans leaving a football stadium or people walking in an airport over some suspended platform where, because of some interaction between people and a flexible or moving walkway, the thing starts to oscillate and then sometimes it can actually collapse. So it's a very mysterious aspect of civil engineering where human beings interact with structures in the environment that we haven't quite figured out. It's some kind of combination of biomechanics meets civil engineering, and it's a very active, interesting part of science and engineering today. Now, so here's my last point, which is that the firm that built the bridge, a big Danish engineering firm called Eric, decided to try to understand what was happening, and they put their own employees on the bridge. So in the experiment, what you're seeing here in blue is a systematic ramping up of the number of people on the bridge. So first there are 50 people, they walk for, I don't know, like a minute or something. This is in seconds, so 100 seconds or whatever. And they're measuring the acceleration of the bridge sideways in red. They got accelerometers on the bridge. So you'll notice that as more and more people get on the bridge, the red gets a little bit higher, but nothing particularly dramatic until they have 166 people on the bridge. And then you see this exponentially growing oscillation. There's a phase transition happening at a critical number of people. This thing that Winfrey more or less anticipated 60 years earlier in a totally remote part of science about biological rhythms. Okay, so I'm trying to get across the unity of science here, that if the math and known for thinking about biological rhythms were part of the everyday education in civil engineering, maybe this kind of thing would be less surprising. In any case, it's a remarkable example of the kind of phase transition that we're trying to understand, those of us that study the dynamics of coupled oscillators. So let me leave you with this thought, that I hope from the talk it's been clear that the study of sync is extremely interdisciplinary, and I'm really honored to be able to give this Sowers lecture because I sort of feel that's the spirit behind the lecture, that we're all here together talking about math and science and engineering and all parts of those subjects because they all come together. It's one world out there, and we really need every bit of help we can get to understand it. So let me dedicate the talk to my mentor, Art Winfrey, who I've been talking about. That's actually a picture of us when Art thought it would be good for me to go down a whitewater river in a raft. That's him on the right, me on the left, earlier model of myself there. And I hear from John, what is your river here? What's it called? New River. New River. Apparently you have a river like this too. I mean, we didn't raft it, we didn't paddle. We had some big bruiser doing the rowing while we were holding on like that to the raft. But anyway, so unfortunately Art died some years ago, but I still miss him every day, and just wanted to dedicate this to his memory. Okay, thank you very much.